Okay, let's get started. So we can see that, very good. Okay, so so before we briefly review what we covered in our last lecture, so let me see. So basically, you can see the website of the class, and you can see all the Canvas pages now, right? So normally I use pages under Canvas in Canvas, right? You can see all the course. Let me see whether I can show you. So this is basically on Canvas, right? So no, yeah, I put everything under pages. You can see we have lecture notes, lecture slides, and lecture video, and the syllabus. So as we said before, so slides basically mainly for review of the previous lecture's content, okay? And you can see we have our first lecture here already. And for lecture notes, we don't have any lecture notes yet, right? So we're gonna have something today, okay? And you can also find all of those under file, okay? So now we just have the slides and the syllabus, right? So this is one way to review all the course content, okay? And let's see whether whether the video works or not. So this is a video. Why it look like that? Huh? Private? Oh, I didn't put that public yet, probably. Yeah, so this is our first lecture video. So let me see. Here, publish, public. Okay, and now you should be able to see that. As we said before, so we're gonna have two sets of video, right? One is this EEL6532, our class, right? So this is a recorded lecture, and this one is my old lectures. Okay, so yeah, feel free to watch either of them. So in the old lecture, I may go things in a bit more detail because I don't have a time constraint there, so I just go over everything. But in our lecture, so it could be a bit different, and also the course content will be updated a little bit according to what is very popular now. It's artificial intelligence, right? So okay, and the other thing is our course website. So the course website will be exactly the same as the Canvas. Okay, you just need to watch either of them. Okay, here we have syllabus, we have lecture notes, and we have video here. Just click it if you want, right? So the website, the URL is in the syllabus. You can see. You can also find it here under my website. So this is my website, and under teaching, and then we have this course here, right? So you can just find it from there. Okay. So any questions for the logistics? Okay, great. Yeah, so if no question, let's go over what we covered in the last lecture. We didn't, we didn't cover a lot in our last lecture. So basically, I introduced myself, I introduced my lab, right? And then we mentioned that information theory is probably the most fundamental theory in many things, right? Including communication theory, including compression storage, including statistics, probabilities, and also artificial intelligence, and many other things. You can see here, actually, you can find this figure from our textbook. Okay, and yeah, and then we went over the syllabus. I will not repeat that here. Okay, and then we'll give a very brief introduction about information theory, right? So basically, for information theory, we want to answer the following, at least want to answer the following three questions, right? Number one, what is information? So we kind of mentioned that in our last lecture. We say it's kind of uncertainty, right? So if we make something from uncertain to certain, basically it means that we gain information, okay? And we didn't talk about how to measure information yet, right? We just briefly mentioned some examples, like flip a fair coin or an unfair coin, right? So we're going to repeat that today, okay? And then we say, okay, so the original version of information theory is basically to answer two questions, right? So one is can we represent information in space, and the other one is how to represent information in time, right? The first one is related to communication theory. Basically means that how we can communicate information from one location to another location, right? And the other thing is representing information in time. So that's basically means storage, right? How can we record all the information or all the data, okay? And so we can draw a diagram here. So it's a communication system. In the communication system, we have both, right? So we have the information source, so which should be stored somewhere, right? And we have our transmitters, and we have our channel, we have receivers and destinations, okay? And if we consider the source information and the destination here, basically is a compression problem or storage problem, right? So basically we want to compress our information as much as possible to save some storage space, right? So in other words, it basically means that we want to remove redundancy, right? So if there's some redundancy there, we don't want it, right? On the other hand, if you consider here from the transmitter to the receiver side, so it's a communication problem, right? And here we want to add the redundancy, right? Because the channel can distort our information by putting more redundancy there. It basically means that we can recover what we transmit back, okay? So we're going to cover, so those two topics are pretty, may occupy maybe around 60% of our class, and then we're gonna talk something else, okay? And yeah, as we said, modern information theory is much more than this, right? So we have security, we have safety, we have private information retrieval, and we use information in artificial intelligence and many more, okay? So we may touch a little bit on those topics as well, depends on time, okay? So this is pretty much what we covered in our last lecture. Any questions? Great. Okay, so yeah, now let's see how we can do this. So I will share my screen here. Okay, great. Okay, and this is normally how we give lectures, right? So I'm going to write everything here, and then hopefully you can follow it, right? So I will share all my lecture notes online for sure, right? But I still encourage you to, write something down, right? Because so if I skip something, it will be useful. All right, so let's get started. Yeah, the writing feeling is not very good. There's too much friction. So I use a paper-like cover. So, but I think this tip also have some friction. So, yeah, too much friction. Okay. Today, so we have two topics. The first one is we're going to answer again what is information. And the second topic is that we're going to answer how do we quantify or how do we measure information. Okay, can you see that? So do I need to turn on the light a little bit, or you're okay?
Can I turn it off?
Yeah, you can. Yeah, just to make sure you can see everything. So yeah, it's on the iPad. It's bright, right? So it's no problem for me. Yeah, that better?
Should I turn off all the
Yeah, what do you think? Want to turn off the light or no?
Okay.
Is that okay? Okay. Yeah. Yeah, just let me know, if it doesn't work, so we can always change. It's not a big deal. Oh, and the other thing is that, my writing, I don't know. So some people say my writing is very good. Sometimes some people say it's not. It's not. Then, if you cannot see what I'm writing, just stop me and ask questions. Okay. So hopefully we're good. Okay. So. The first topic: what is information? Okay, as we said, information is nothing but uncertainty. Okay, so it basically means that want to see how uncertain we are about the outcome of some random experiment, right? So the information theory, is built based on the probability theory, right? So yeah, that's why so in the syllabus, I think in the prerequisite, I think ask you to not me actually. So normally the prerequisite is to ask you to know random process or stochastic process, but it may not be super necessary, but you do need to know probability. Okay, so that's very important. Okay, but we're going to go everything into very detail. You're going to see what we mean by that. Okay, let's write it down. So basically, we need to know how uncertain yes, a pen. I feel very good. Yeah, there's no ball pen option here. So if I change to the pencil, it looks very weird. Yeah, pen, the line are not extremely even. So yeah, let's see. So how uncertain we are about. Yeah, do you mind to close the door? Yeah, thanks. Outcomes of random experiment. Okay, so as we mentioned last time, so the most typical random experiment we care about, or we always give this kind of example, is flip or toss a coin. Okay, so let's see some example here. So basically, so one good example is to toss a coin. Okay, and the outcome would be whether it's a heads or a tails, right? And here we consider two cases. One is we toss a fair coin, and the other one is to toss an unfair coin, right? So let's see. First example we're going to see is that, so let's assume the coin is fair. Okay, it's fair basically means that it's unbiased. Okay, unbiased basically means that the probability to get a heads and the tails are exactly the same, right? So which is what? So the probability of heads, the probability of heads equals the probability of tails equals to what? If it's a fair coin? 50%. Say again? 50%. Exactly, that's half, right? Oh, by the way, so yeah, maybe. So do you know? Normally, when we talk about probability, so what are the three key things to define probability? Yeah, and when we talk about yes.
Like the three axioms.
Yeah, say it. I see.
Like probability of everything is 1. And
exactly.
Probabilities are non-negative, and then if you have a bunch of events or something, and then it could be infinite or countably infinite, and then you take probability of the union of that equals, and they're disjoint, probability of the sum of each one. So
very good, very good. So I really follow him. So if not, just see the definition of probability, right? They're like three axioms, okay? So another important thing, can help us to understand it better is that, when we define a probability, so it's defined on a sigma algebra, right? So anybody know what a sigma algebra is?
What?
Sigma algebra or sigma field. Yeah. Oh, you know that? Okay, great.
Kinda. I don't remember the exact definition stuff. I know that it's like this sort of construction that is like closed under countable union and intersection or something. Yeah, it's just something that works nice. Then you can do like measures and stuff on it.
Very nice. Very nice. Very nice. Yeah, what he said is probably the number 3 axiom, the most important one. So the number one, the first one is that we need to have a sample space, right? For example, if we want to flip a coin, the sample space is what? It's heads and tail, only 2. Okay, that's all the possible outcome. Okay, or yeah, more or less. Okay, and the other thing we need to define is event space. So what is the event space, right? For example, let's say if we flip a coin twice, okay, heads, tail, 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 heads, those would be the 4 events. okay, and the event coming from the sample space. Okay, yeah, those are not extremely important to really understand it, but later on when you learn very deep things, that can be very helpful, right? So what's your name?
Mark,
Mark, okay. So what's your major?
computer engineering.
Very nice. Yeah, I think this kind of theory is almost nobody really cares about it, right? So normally when you learn probability or random process, they will talk about that maybe in the very first class and then forget that forever, right? So nobody can answer this question in my class before. So you're really amazing. Computer engineering, so you are building computers, right? So do you use a lot of math?
Not really.
Hmm.
I like it.
Very nice, very nice. I'm very impressed. Okay, great. Yeah, let's go back. It's a bit far. So when we need some knowledge from that, I'll cover. Okay, now we just want to see some examples and intuitions. By the way, so information theory, we mentioned that in our last lecture. So somebody, if you don't really understand it, so it feels extremely mathematical, it's pure math. Okay, but what is more important than math is idea. Okay, we really need to understand how Shannon think about all the problems. That's much more important than the math. Okay, math everybody can follow, but how does he, come up with all the math? So that's the most important thing, right? And then we need to understand that. Okay, so yeah, and now we're just coming to the intuition here. Okay, so this is the case where the coin is fair, right? But when the coin is unfair, right, or when the coin is biased, okay, then what will happen, right? So in this case, the probability of heads and the probability of tails. Why there's a line here? I'm using this. It's called what app? Good Note, something like that. So I never used that before. So I have to pay that every month to use that now. So, but I don't need any advanced feature. So. Okay, so when the coin is biased, then it means that the probability of heads, probability of tail, they're not equal. Okay, so let's give more extreme case, right? Let's assume that the probability of heads is what, 1/10, and the probability of tail is 9/10. Okay, so it's a very biased coin. Okay, so now we have these two cases, right? And based on our understanding, right? I gave this example before in our last lecture. So I have two cases, right? So which one, if we do this experiment, just flip the coin once, okay? And which one you get more information? In other words, which one is more uncertain? The first case or second case? First case, right? Why is that? Because in the second case, probably it is head, right? So if I'm telling you it's a head, it does not surprise you, right? But it's just intuition, right? We cannot rely on that. But if I tell you it's a tails, then it may surprise you more, right? But so based on the common intuition, the first one is more uncertain, okay? So this one is more uncertain, okay? Therefore, we think this one may contain more information, right? So that's basically the intuition. Where's add page? Add a page to the outline. Oh, it should be this one. Okay. Root. Oh no. Yeah, there are too many options. I don't need those options. So I want it wide. Apply. Okay, good. Okay, so next let's talk about how do we measure information, right? That's a very important concept. Normally, in very first class information theory, so I'll just give you, the definition of entropy, so which is how to measure information, okay? But now, so what I'm going to do is that I'll follow Shannon's original paper to tell you how come he comes up with this, okay? Let's see how we can do this. Okay, here I have to introduce some notations from probability, okay? So we consider a discrete random variable. Okay. We consider a discrete random variable. So here we use notation of capital X, okay, to determine, to decide, to define it's a random variable, right? And all the values of X, we define that in a discrete set, okay? So that takes values in a set, okay? And normally we use calligraphic X to represent this set, okay? Or, you know, if it's not a random variable, you can think this as like the sample space, okay? All the possible values of X, okay? Or we can think about it as a set of outcomes, okay? And then the event, okay, so because we consider a random variable now, it's not like a particular event. It's not flip a coin, right? So it's just some random variable with some values. So therefore, the event here basically means we need X to take some values, right? So the event will be something like this. It's a set that capital X equals to a value, a realization. So we use that. We use small x to indicate that, okay? So this basically is the event that capital X takes on the particular value, small x, that is in the set of X, right? So now we have capital X here, and we have calligraphic X here, and we have small x here, right? Small x realization, capital X random variable, and the calligraphic X is the set of all the outcomes. Okay, yeah. Okay, yeah. And so now let's map this to our previous example, toss a coin, right? So we want to toss a coin, okay. Then basically we need to assign the values to each of the events. Okay, so now our calligraphic X, so which is a set of all the outcomes, so we let that be 0 and 1, right? Because we have only two outcomes from one toss of a coin, right? So we just use 1, 0 there. You can use whatever you want, right? That number doesn't matter, okay? And then we can say that if capital X, which is our random event or our random variable, if that is 1, then they can mean, again, you can assign that to whatever you want, right? So I assign that to probably, so this means the outcome is tails. Okay? Yeah, so basically, yeah, that's how to map this, the probability, you know, to our previous example, okay? And then based on this, so we can have our probability mass function or PMF, okay? So normally when we talk about PMF, it means that we work on the discrete set, right? Or here we say it's discrete random variable, right? Discrete basically means that it takes for in some discrete numbers, right? So we can assume that the total number that we can take there is finite, okay? Countfully infinite is totally fine, but so we're talking about finite numbers here for simplicity, right? So we have, so from here we can define the probability mass function, the PMF of X. Okay, so that is basically the probability. Okay, so here again, notation-wise, normally in this class, we use small p of x, small x, right? This realization. So that's basically equals to the probability that capital X equals to small x for all small x in the set of X. Okay, so that's our notation. Okay. And here, clearly, if 1 is tails, then 0 will be heads. Okay, so this is tails. Okay, so this is our example. Okay, and based on that, based on all the notation here, right? So we know what is the probability. So now we're ready to kind of think about the measure of information. So measure of information is a pure function of the probability. That's it. Okay. So again, so here we consider probability mass function because everything is discrete, right? If things are not discrete, then we use PDF, probability density function. Okay. This PMF is easy, right? Because it just defined this way: probability of x equals to x equal to. So that's our PMF. Okay. So later on, the reason we start from here is that not only because it's relatively, easy to think, and the other thing is we have very rigorous meanings for the discrete random variables. When coming to the continuous random variable, so how can we define information or how to measure information becomes almost infeasible. Okay, but we still have a way to deal with that. But so we're going to talk about much later, so in this class. You may think a little bit, right? So why, if I have something that takes value on the discrete set, so that would be the easier to think about how much information we can gain, right? It's not very hard to think about, right? For example, let's say we have only 2 cases, right? So if we know the result, we know that it has to be 1 out of 2. Okay, but if it's continuous, it can take whatever values in a range. Then if we get 1 point or get some range, how can we think about this problem? It's not straightforward if you think about that. Okay, yeah, let's see. Okay, and based on that, so we're going to denote this h of x. Okay, so here we need to be more careful. Yeah, x is a weird letter, right? Everything looks identical. So capital X is a random variable. H of capital X, so this is the measure of uncertainty of x or measure of information. Okay, so denote h as the measure of uncertainty of capital X. Okay, and here, as we said, we want to assume that the total number of outcomes is finite, it's n. Okay, and in addition, as we mentioned before, so we consider h of x. So clearly, if we read in this way, h of capital X, it means that h is a function of x, right? But more implicitly or explicitly, so hx is a function of the probability mass function of x. Okay, therefore, we can also write h as the function of all the probabilities, right? So h of x is a function of PMF, px for x in this x, okay? And h is called entropy. Or, entropy is a definition from physics, right? Thermodynamics, right? So who learned entropy before from thermodynamics? Only 1, 2?
I forgot.
Yeah, that's why I ask you who learned, not who remember it, right? Normally, that's how yeah, so actually, if you think about that in thermodynamics, it's kind of, the idea is borrowed from there. So it's also a measurement of uncertainty, okay, how the particle move, something like that, right? Yeah, but if I said anything wrong, then, yeah, I don't understand. I know nothing about thermodynamics, so. Okay, great. Okay, so this basically means that we can write down entropy as a function of, let's say, px1, px2, px3, and so on until Pxn, right? The key here is that think the uncertainty, the entropy, as a function of the probability distribution, okay, or the probability mass function. Okay, that's very important. Okay, so now the question is that what is H? How can we compute H? Okay, as I said, normally, I'll just give you the definition of H, right? And then you remember it in the rest of your life, and then you're good, right? But that's not coming from that, right? So we have a strong intuition how we derive it, right? As the normal math, right? So we need some axioms, right? So we need something that we all agree with to define or to compute entropy, okay? So I have 4 axioms to cover. Some of them is easier to understand, some of them is not. So let's see the first one, axiom 1, okay? So we need to start from somewhere that we're really familiar with, which is to toss a coin, right? I think that's a very simple example. As I think we kind of understand that. So now let's consider a fair coin, okay, or an unbiased coin, okay. So we can write down the entropy of event of toss a coin as H of half and half, right? So this is a probability, right? And what do you think? So we want to give a number there, right? You can give any number there, right? But which is the number that kind of make most of the sense, right? So in this case, x equal to 0 and 1. So if we do this experiment, right? So we get the outcome from 2 possibilities, okay? So what do we do with that? 0, 1, what do you think? Do you see that before in anything? Storage, communication, machine learning? Do you see 0 and 1 all the time? Yes, right. What do you call that? Bit, right? We just say that equals to 1 bit. Does that make sense? Does that make sense? Not really, actually. So we need to go back and forth, right? Why it's called bit, right? So I mean, come on. Yes.
What if it's H like 1 over 10 and 9 over 10? Is that still equal to 1 bit?
Yeah, that's a very good question, right? Would that equal to 1 bit? Definitely not. Right? That's why I said half and half, right? So, and we said, in this case, we have more information, right? It's more uncertainty, right? So basically, this is something we agree with, okay? I think this is kind of, it's magical, but it also comes from intuition, right? So basically, if we, only 2 possibility, right? And if, we don't have a preference, right? Yeah, it's just, it should be like 1 bit probably, right? But we're going to back and forth, right? There's something we need to, understand it. But it really doesn't matter. It could be 1, it could be 2, 3, 4. Pick a number you like, As we said, we just need a number there, right? If this number is not 1, we just normalize it, divide it by 2 or whatever, right? It's a different unit, right? We're going to say that, okay, bit is some unit. We can use some other unit. Then this is not 1. It's some other number. It doesn't matter. We just need a number there for now, okay? And also, this bit is normally called information bit or Shannon bit, which is different, actually, from the bit that we understand. Okay, definition is different. Okay. Second axiom. Okay, so this one I think is relatively easy to understand. So we denote small h of n equals to capital H of 1 over n, 1 over n, 1 over n, so on. Okay, so how many terms do we have here?
10.
10? N, exactly. Right, because it's 1 over n, right? If it's 1 over 2, I have 2 terms. 1 over n, we have n terms. We need to make sure the summation of all of them is 1, right? We have n terms there. Okay, so we say this guy. Okay, I should use. We say this guy, this function. So if we write in this way, h of n, it means that we think that as a function of n, right? And for this function, if we increase n, and then what do you think? Do you think the value of this function is increased or decreased or don't change? Right, let's think about examples. Increases. Any different opinions? Right, let's think about, right? So if if for this one, if I have something else, right? We have 3 outcomes happen with probability 1/3, and then compare that to this guy. Intuitively, which one is more uncertain?
3.
Exactly, right? Then you're right. So this one is bigger than that. Okay, it basically means that, so this function, small h of n, is a monotonic increasing function, right? Yeah.
I have a question on axiom 1.
Yeah.
So does it mean that there's no infinite entropy?
There's no infinite entropy.
Like, is that what axiom 1 is telling us?
Yeah. Let me think. No, definitely not. In this case, if the total number of outcome is finite. That makes sense? Yeah, it will make sense very soon. Yeah. Yeah, it's finite. It's not infinite. Very good question.
But is that what axiom 1 is telling us? No.
Not really. No. Axiom 1, no. Axiom 1 only tell you, so the entropy of that is 1. That's it. Or some other constant, doesn't matter, right? And so, we're going to have 4 axioms. Applying all of them, you can conclude the value of entropy is finite. If, this small n is finite, right? So if that is finite, no, it's not. Okay, but later on, there will be a lot of very weird things happen. So you'll see. But it's very good to understand everything now. Now it's not messy. So let's write it down. So small h of n is a monotonic. Non-decreasing function. And okay, very good. So so this is the second axiom. So let's talk about the third one, A3. So, by the way, so what is the axiom? So it's something that we all agree on, right? There's no proof of it. You have to accept that. Okay, based on intuition. Okay. And for the third is that we assume that h of x is a continuous function of PMF. Okay. You'll see why we need that. It's so it's a continuous function of Px. Okay, so any different opinion on that? Yeah, it's very important. So the reason we need that, later on you're going to see that, so in case the probability is an irrational number. Okay, so when the probability is an irrational number, we need this condition a lot. Okay, otherwise we don't need that. So if the probability or the PMF is a rational number, right? So what is a rational number?
What is it, what?
Rational number. Rational.
Not infinity. No.
Integers.
Exactly.
Fractions.
Exactly. Any number can be written as this. And n and m are all integers. Right, so that's rational. So when, the probability are all rational, then we're fine, we don't need that. But when it's irrational, then something can get tricky, right? Then we need that. So this is not super important. I think all the A1 from A3 are pretty intuitive. Okay, so there should be easy to accept, right? But XM4 is not. Or, it's not that trivial. So XM4, we need some harder work to explain that, right? It's called grouping property. So what's grouping property? So let's give you the simplest example. Okay, we consider this calligraphic X set. We have 3 values, 1, 2, and 3. Okay, so now we're going to do as follows, right? The first step is that, so we're going to group 1 and 2. Okay, consider 1 and 2 as one event, as a single event. It means that if we run the experiment, we get either 1 or 2, then that belongs to the first event. Okay, and the second event is 3. Okay, So now let's compute. So what's the probability of this event, right? Again, so when you assign, let's say the probability of this is P1, the probability of that is P2, the probability of that is P3, right? So what's the probability of this one? The grouping 1, 2 together. So what's the probability of that? P1 plus P2, very good. What's the probability of that? P3, right? So that doesn't change. Okay, very good. So this is the first step. We group, some event together. Secondly, the second step is that, so now we are going to look at this event, okay? The grouped event, 1, 2. Okay, for this 1, 2, we still have 2 events there here, right? So now, let's given the fact that, this is a conditional probability, right? Given the fact that P1, 1, 2 happen, right? So what's the probability of the first one?
P1.
Is that right? Let's say given 1 and 2 are happening, right? The trick here is that, so this is called, Bayesian rule. So what's the probability of this guy?
Half times, it's like probability of A given B.
Exactly,
Like
exactly,
probability of
exactly. Yeah, conditional probability.
times probability of B given A divided by probability of A.
Very good, right? Yeah, let's write it down, right? So now what we're computing is the probability of 1 given the probability of 1, 2 is happening, right? Okay, this equals to what? So the probability of 1 divided by the probability of 1, 2, right? So what's the probability of 1, 2? What's this probability? We just said, right? So it's this guy, the grouped event, right? That's P1 plus P2, right? And the probability of P1 is P1. Therefore, given 1, 2 happening, and then the probability of this guy is P1 divided by P1 plus P2. Does that make sense? Yeah, Bayesian rule. So, and similarly, the probability of 2 is P2 divided by P1 plus P2. Okay, any questions? Yeah, that's very important, right? So basically, yeah, if I tell you, 1, 2 is happening, basically it means that 1 or 2, of course, 1 or 2 is happening. Basically, okay, 3 didn't happen, right? Then the probability increases, right? How it increases is to divide by P1 plus P2, okay? So that's Bayesian rule, very good. Okay, great. So now we have these 2 steps, right? First one, we group 1, 2 together. Second one, given 1, 2 is happening, and then we get a probability of 1 and 2, right? So now let's see if we do this, how can we use this idea to compute entropy, okay? Yeah, let's see whether this makes sense to you or not. So now our entropy in this case is P1, P2, P3, right? So I have 3 probability, okay? And so let's do this, right? So clearly, we have this here, right? So this random experiment already have some entropy, okay? So the entropy of the first step is nothing but h of what? P1 plus P2 and P3, right? So this is the entropy of the first step, right? The entropy of the first step, okay? So now we need to add on the entropy of the second step. Then we can find the entropy of this guy. Does that make sense? Okay, so this is easy, right? So this is the entropy of the first step. So what's tricky is that what is the entropy of the second step, right? So we know the probability of second step definitely have the entropy of P1 and the P2, right? So because that's the entropy of this event, right? But the trick part is here is that, yeah, sorry, it's not P1. Yeah, how can I say it? Yeah, I'll restate it. So, yeah, if we just look at this event, okay, the probability of that is this guy. The probability of that is this guy. Therefore, we know this entropy is P1. P1 divided by P1 plus P2, and then P2 divided by P1 plus P2, right? But it's conditional entropy, right? So what we need here is that we know this event, 1 or 2, will happen with this probability, P1 plus P2, right? Then we need to multiply this in front. Okay, this basically means that, okay, as a first step, so we have this entropy, right? That's good. And for the second step is that, okay, so with probability P1 plus P2, and then the second step have this amount of entropy. Does that make sense? Right? Let's go back, redo it. So the first step is to group things together, right? Clearly, the entropy of that is this guy, right? I think that's no question. The trick part is the second part, right? The second part, when we consider second step, we have to pick either 1 or 2, right? That happens with the probability of P1 plus P2, okay? And with this probability, we know P1 or P2, one of them is happening. And then the entropy of that is the entropy with this probability and this probability. Does that make sense? Yes?
So because the outcome is more certain, the entropy will be lower, which is kind of represented by that multiplication by the
Yes.
probability in the front?
Yes.
Okay.
Yeah, I think so, yes. But again, it's not a mathematical proof. It's an axiom. So this is something intuitive, coming from intuition. We agree on that, and then we derive something else. Okay? So the only thing we need to make sure is that this intuition makes sense to you. Does that make sense? Yeah, this should be pretty, Yeah, go ahead.
Yeah, so why do you multiply P1 plus P2 as a probability?
Yeah, because the second step happens with probability of P1 plus P2, right? Because when we're coming to here, only when either 1 or 2 is selected. Okay, right? So if no one from 1 to selected, then we don't worry about that too much. But this happens only when 1 or 2 is selected, right? That with the probability of P1 plus P2. Right? We can think in that way, at least. Does that make sense?
So you multiply P1 plus P2 in the front, and that means, so you multiply a probability to an intrinsic, but the intrinsic is a function of probability. That means
yes.
It's kind of confusing me, like the probability times a function of.
Yeah, H is to measure information, let's say. I phrase it this way. Right? The only thing you need to make sure is that, okay, the second term, it will make sense with the probability of P1 plus P2. That's it. Right? Otherwise, you will just add it, right? So 1 happened with the probability of this, and 2 happened with the probability of that, right? But that only under the, when either 1 or 2 happened. Okay? Are we good? Yes.
So H, P1, P2, and P3 is like the add. So what is the plus sign over it? Like, do we add?
Yeah, add these two together.
Oh, okay.
Yeah, so this guy plus this guy. Yeah, so that's okay, great. So this is the grouping property. It's just a simple example, but we need to generalize it a little bit, right? So in general, okay, let's say we have n terms here. I have HPX1, HPX2, up to HPXN, right? And if we only group the first 2 terms together, okay, so that will equals to what? HPX1 plus PX2, okay, and if we do not change the other terms, PX3 until PXN, right? So this guy will equal to this, and then plus when Px1 and Px2, either of them happens, and multiply the probability of the rest, right? The rest is what? Same, right? Px1 divided by Px3, Px1 divided by Px1 plus Px2. Right, let's make it more clear. Plus Px2 divided by Px1 plus Px2. Okay, so this is exactly the same as that, but we consider more possibilities here. Okay? Any questions? Okay, great. So next, so we don't have too much to cover that, but I'll just start it. So now we can generalize it to any kind of grouping, right? So we can group, in the way that we want. Okay, so we just consider the most general case, generalized grouping axiom. Okay, so this is our real A4. Okay, so this is our A4, axiom 4. Okay, so now we need some complicated notation here. So for all the possible of outcomes, we have two indices. One is grouping indices. The other one is the indices in each group. Okay, so we can do the first one here, I from 1 to k. So this is our group indices. Okay, and the other one is j, is from 1 to, we use mi to tell you, okay, now this is in the S group. Okay, and each group have mi's numbers as mi's element. Okay, mi can be anything. Okay, so yeah, this is the index of elements in each group. Okay, very good. And we're going to start from here next class. Okay, thank you. Yeah.
Should I go there? So ask you, I have a question.
Yeah.
Yeah, so
Yeah, you can whatever.
as far as I know, like, as I can tell, like, so is the grouping like nested probabilities? What do you mean about grouping?
Oh, group.
Nesting?
Yeah, maybe. Yeah, I'll show you here. Yeah, I'll talk about that in detail for sure. But grouping just like this, right? Group 1, 2 together, right? Or you can group 1, 3 together, 2 and 3 together, whatever. Yes.
Like in an example, that would be like if you have.
Yeah, maybe. Yeah. If I have a bit time, I'll cover an example here.
Okay.
So yeah, that's exactly. Yeah, for example, let's say we have 4 groups. The first group, second group, third group, and the fourth group. Yeah, the group can be arbitrary. For example, first group is x11, x12, right? The first index is the group index, second one is the element index. And second group we can have, for example, x21, x22, x23, x24, and so on. And third group we can have from x31, x32, x33, and last one could be x41, x42, and so on. In total, we have like how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We have 11 number of outcomes. Yeah, we can group whatever we want. Right? This is one example of how we group. Yeah. Yes.
I have a question about axiom 1.
Oh, by axiom 1?
Yeah.
Very good.
I believe this gentleman here asked that if the probabilities were 9/10 and 1/10,
Yes.
would it still be a bit? And you responded no.
No.
But why would that not be a bit? Because the outcomes are always either.
Yeah. Yeah, because it's less uncertain, right? Yeah, let's say if the heads happen with probability 1/10, and tail happen with probability 9/10, with high probability, it's a tails, right? And this is a common sense. It's like axiom, right? So but yeah, we didn't say that's axiom. Actually, we can derive it from these 4 axioms. Later on, you're going to see that is not 1, but we cannot get it is not 1 from axiom 1. So axiom 1 only tells you this is 1. But if it's h of 1/10 and 9/10, what's the number of that? So axiom 1 does not tell you that is not 1. Maybe that is still 1, but turns out it's not 1. Yeah, but yeah. So we want to assume as less as possible. Yeah, very good. Thank you.